Hello, we're going to be getting started with our next session, Greetings from the Future, Part 1. All right, thank you. Okay, Anna Crawford is going to kick us off with a talk on high-fidelity modeling of marine ice cliff instability shows mixed mode ice cliff failure and stabilization from millage.
Hello, thanks very much for having me join you as a virtual guest today. My name's Anna Crawford. I'm based at the University of St. Andrews and am a postdoc with the International Thwaites Glacier Collaboration's Dominoes project. And today I'm presenting results of an idealized modeling study that I conducted with these excellent co-authors. And this study looked to improve our understanding of how these hot topic processes of ice cliff failure and marine ice cliff instability could transpire. Ice cliffs, which will be exposed after ice shelf loss, can maintain their integrity up to a certain height due to the cohesive strength of ice. However, as the ice cliff increases in height, that longitudinal strain will at some point overpower the ice's finite strength, and this could lead to an ice cliff failure event. The daunting self-sustaining marine ice cliff instability would initiate if increasingly tall ice cliffs are exposed with each of these one-off ice cliff failure events. And this risk heightens if retreat progresses over a retrograde bed into regions of very thick ice. And we'll discuss more factors that could lead to this initiation occurring or not during the talk today. In the often referenced work by DeCanto and Pollard and company, we do see alarming retreat of the West Antarctic ice sheet when ice cliff failure is represented in an ice sheet model. And from these alarming projections, we can see why we need to accurately represent ice cliff failure in these models. But improving this representation is going to necessitate improving our own understanding of how ice cliff failure will occur. And this so far has been challenged by a lack of observations and the assumptions that we need to make regarding stress thresholds when we rely solely on continuum modeling. With these needs and challenges in mind, our project employed a suite of high-resolution 3D glacier models with three aims. We wanted to investigate the process itself. We wanted to derive a solution to represent this process in ice sheet models. And we wanted to assess what factors and processes could potentially counter retreat via marine ice cliff instability. Our model suite consisted of three models that we used individually as well as in coupled workflows. We used the full-Stokes continuum model Elmer ice to model the viscous deformation of our idealized glacier calving faces. And to see if and when ice cliff failure occurs, Elmer ice was paired with HIDEM BE, which is the standard brittle elastic implementation of the Helsinki discrete element model. And this numerical calving model represents glaciers as assemblages of densely packed discrete particles that are bonded by elastic breakable beams. HIDEM BE has previously been used to explore tensile fracture. And in this study, we also explore shear failure with HIDEM BE, and we do that by adjusting parameters that influence micro damage and shear strength. Our final model is HIDEM VE, and this is the brittle viscoelastic implementation of HIDEM, and we employ it on its own to investigate viscoelastic flow and ice cliff failure. In HIDEM VE, particles are still connected by breakable beams, so it still captures that brittle elastic component of ice deformation, and attractive forces applied to adjacent particles mimic viscous deformation. So the first mode of failure that I looked at was when viscous deformation led to brittle failure, and I used this with the Elmer ice HIDEM coupled workflow. And this mode of failure applies to undamaged ice that is strong and shear. And we see with the Elmer ice simulations that we have this forward lean of the calving face, we have surface lowering, and we have bulging along the water line due to the concentration of stresses in this region. And when we take this Elmer ice deformed geometry and use it to initialize a HIDEM simulation, we see that tension resulting from that forward lean results in surface crevassing and calving via forward block rotation. And this workflow uniquely allows us to explicitly determine how long it takes for that failure to occur and what the magnitude of that retreat is going to be. Time to failure and retreat magnitude were found to scale with cliff height, and this leads to retreat rates that increase non-linearly with the height of these ice cliffs. We found that calving rates increase with warmer ice. So if we're looking from the blue to the black to the red lines here, and that's due to the impact of temperature on the rate of viscous deformation, with warmer temperatures increasing that deformation rate, which allows these glaciers to more quickly reach that critical angle of forward lean at which tensile failure occurs. We also found that increasing the basal slip decreases the retreat rates. So if you compare the blue to the pink lines here, as that critical lean angle was reached less quickly or not at all, as that glacier's base is more or less able to keep pace with that cliff lean. So now I'm going to look at shear failure, and the figures on the bottom here show failure in HIDEM when the interparticle beam width is decreased or when micro damage is increased. And we see in both the formation of shear bands, we see slumping at the surface just behind the calving face, and we start to see buoyant uplift occurring. We find that there will be a transition at some point between tensile and shear failure, but we did not feel that we could confidently quantify the time to failure for this mode of failure. Importantly, though, these descriptive simulations highlight the conservative nature of the time to failure values reported for the viscous deformation to tensile failure simulation series that I showed on the previous slide, because we know that failure is quickened once the shear failure sets in. Lastly, we conducted simulations of viscoelastic flow with HIDEM VE. When applied to the same model geometries as I was showing for simulations previously, and with limited basal slip, HIDEM VE simulations showed a pattern of waterline bulging similar to what we were seeing with the Elmer ice simulations earlier. However, we also see pronounced shear bands emerging up glacier from the calving face, and this was seen for the greatest thicknesses simulated with HIDEM VE. A second set of experiments applied HIDEM VE to a domain that approximated the grounding line region of Thwaites Glacier without any fringing ice shelves. And the failure of the thinner domains was dominated by vertical crevassing, and this crevassing was induced by the tensile stress caused by stretching that resulted from greater basal slip. Brittle compressive failure caused shear band formation and slumping to become the dominant characteristic of the terminus collapse for the very thick domains tested with HIDEM VE, and this resulted in the rapid formation of a very dense melange. Our work on viscoelastic processes is continuing now, and a colleague of mine named Jan Ostrom is using a 2D viscoelastic model that is letting us more finely interrogate the thickness thresholds at which these concentrated viscous stresses lead to shear failure. I'd like to take a moment just to review the different modes of failure that I just went through on the previous slides. First, glaciers with undamaged ice that is strong in shear and exposed to limited basal slip are shown to characteristically deform through surface lowering, waterline bulging, and cliff advance, and the resulting overhang imposes tensile stresses that can cause collapse via brittle failure and leading to distinct iceberg calving events. We also see tensile failure through numerous full thickness crevasses when glaciers of intermediate thickness with greater basal slip are simulated in HIDEM VE. And if we can think of that viscous deformation leading to tensile failure being kind of one end member of the modes of collapse, then ice cliff failure via shear band formation can be considered the other end member. And this dominates for thicker, weaker glaciers and is displayed through shear band formation and slumping. So you will remember this plot from earlier. It is showing the retreat rates derived for the viscous deformation to tensile failure mode of failure. And I used this data to fit a simple power law shown here in the upper right that allows us to relate cliff height to a calving retreat rate. And the model parameters are I and alpha, and these are fit to different regimes of ice thickness and basal friction. I note that this law is conservative. It does not include the impact of shear failure, and I was describing earlier how shear failure is going to accelerate the collapse process. And it only applies to an unbuttressed calving front. Right now, there's nothing providing resistive forces to the calving face that could slow this process down. Through simulations of that viscous deformation to tensile failure mode of ice cliff failure, where we included a synthetic melange, we do see that if present and able to apply enough back force to a calving face, melange can inhibit ice cliff failure. And this is also shown in complementary work by Domino's co-PI Jeremy Bassis. So this back force can be introduced through different scenarios of melange buildup and will be very important to consider when including ice cliff failure in projections of ice sheet retreat. That study led by Jeremy used M-ice to tease apart the conditions in which ice cliff failure will occur, when it will lead to retreat or when readvance will be possible, and what conditions could lead to catastrophic collapse, specifically considering thickness gradients, bed slopes, and inflow velocity. He shows that there's a transition at a critical thickness gradient where we see catastrophic collapse via MacKie occur because thicker and thicker ice is rapidly exposed. And this work is complementary to my project's findings, which also found that viscous deformation leading to tensile failure can put a subsequently exposed ice cliff out of that failure regime. So together, our two pieces of work show that ice cliff failure does not always lead to irreversible collapse, as dynamic thinning, upstream ice flux, and the evection of thicker ice will influence the height of newly exposed ice cliffs. So on to the key messages to take home with you. Our idealized simulations illustrate a range of modes of structural cliff failure. We see that dynamic thinning is going to influence ice cliff failure retreat, and especially at cliff heights close to the stability threshold. Once retreating and exposing taller ice cliffs, instability increases rapidly and retreat rates can increase non-linearly. The evacuation or buildup of melange will be a rate-limiting process on retreat via ice cliff failure. And the conservative ice cliff failure retreat rate law that we provide needs to be incorporated in ice sheet models alongside other processes, especially melange production and evacuation. Of course, there's always more work to be done, and our team is now looking into those viscoelastic processes more finely, which I mentioned earlier. We're looking at how these processes could unfold at particular locations, especially thwaites, and we have started some simulations of calving at thwaites with its current configuration. And we are looking to incorporate our retreat rate law in an ice sheet model, and we are doing this now with partners within the ITGC. So thanks very much for listening, and of course I'd be happy to take any questions.
Great. Next, we will have a talk by Trevor Hillebrand on modeling the control of iceberg calving on decadal scale retreat of Thwaites Glacier.
Hi everyone, I'm Trevor Hillebrand. I'm a postdoc at Los Alamos National Lab, and I'm going to talk today about modeling the control of iceberg calving on decadal scale retreat of Thwaites Glacier. Recent work has highlighted the importance of iceberg calving on mass loss projections from Thwaites Glacier over the course of this century. On the left are two figures from a recent study showing these projections of Thwaites Glacier using different calving laws, and these colored curves on the top correspond to the grounding lines at 2100 from these simulations using these different calving laws, and on the bottom are the resultant mass loss time series. And so you can see that what you assume about the calving law really dictates the behavior you get over the course of the century. Now on the right we see this satellite image of Thwaites Glacier, and this illustrates that the kind of damage we're seeing at Thwaites, with rifting occurring all the way to the grounding line and the western ice tongue at the bottom, essentially a collection of rifted blocks, is really not accounted for in commonly used calving laws. So we're asking how accounting for damage will affect multi-decadal projections of the retreat of Thwaites Glacier. To do this, we're using a 3D higher order ice sheet model called MALI, using a regional domain over Thwaites Glacier with a 1 to 8 kilometer unstructured mesh shown on the right. We optimize temperature and basal friction fields against observed surface velocities from measures using bed machine Antarctica ice thickness and bed topography. And we use climate forcings provided by ISMIP 6 using an RCP 8.5 climate scenario, and in our forward runs we use the ISMIP 6 subshelf melt parameterization. To account for damage in our model, we use the formulation of Bassis and Ma, which allows damage to evolve based on ice dynamics and ocean forcing. So in the top panel we have a crevasse initiating in the bottom of the ice shelf, which can then open by plastic necking or melting, or close by creep or freezing within the crevasse. We apply this to our initial condition and spin it up for a year using static ice geometry, we find that our calculated damage field on the right closely agrees with the observed calving front in 2015 shown in this white contour. So everything with damage approaching 100% shown in yellow is really this area of rifted bergs and melange that's no longer a structural part of the ice shelf. We use 4 different calving laws in our forward simulations, the first of which is the von Mises stress calving law, which is widely used but does not account for damage. So this sets the calving rate C equal to the ice velocity times the von Mises stress divided by some threshold stress, which is a tuning parameter. Next, we use a simple damage-based calving law in which we just remove ice that's connected to the calving front where damage exceeds some threshold value. In the third case, we simply combine these two calving criteria, and in the fourth case, we combine them in a more sophisticated manner in which we use the damage as a multiplier on the von Mises stress criterion, and so as damage increases, the effective threshold stress decreases. These are the results of our von Mises stress calving simulations after 5 years. So observations are shown on the left. These are observed velocities from 2018 to 2020, and the observed 2019 calving front in white. Our modeled ice velocities are shown in the middle panel, and our modeled damage is shown on the right. So we see that we're getting an eastern ice shelf in our model that's a bit too fast, and near the grounding line of the western ice tongue, we are greatly underestimating the observed velocities. We also find that we have too much floating ice, and that there's this large area where damage exceeds 90% between the eastern ice shelf and the western ice tongue. So running this forward, we see that this area with significant damage approaching 100% sticks around and indeed grows over the course of the simulation. And so we're showing here that we can't possibly model Thwaites accurately without accounting for damage. Next is this 90% damage threshold scenario. Once again, the observations are shown on the left. And once again, we get an eastern ice shelf that's too fast and a western ice tongue grounding line area that's too slow and too much floating ice. And especially in the grid south here near Haynes Glacier, we see that these very low damage values in the ice shelf indicate that for any reasonable threshold value, this calving law is not going to help us reproduce observations. And as we run this forward, we see significant and probably unrealistic growth of floating ice, including a pinning of the western ice tongue on a new pinning point. In the third case, when we combine von Mises stress and the damage threshold, we suddenly get a very good match between observed and model velocities for the eastern ice shelf within about 2% on average. And but we still have this problem with the western ice tongue being considerably too slow. But we get a good agreement with floating ice. And as we run this forward, we see that now the eastern ice shelf unpins in about 2040 and periodically regrounds on that pinning point, but considerably less floating ice than in previous simulations. And finally, we have the case of the von Mises stress calving law with the damage multiplier. And so once again, our eastern ice shelf is too fast, the western ice tongue grounding line is too slow, but we get a good agreement with ice extent. Running this forward, we see a much earlier unpinning of the eastern ice shelf, and it stays unpinned, starting in about 2036. And this prevents accumulation of large areas of highly damaged ice, and it prevents the significant advance of floating ice everywhere. Now, this issue with the western ice tongue grounding line being too slow has been persistent across all our model runs. So to address this, we've attempted a run in which we couple damage to rheology. And so damage essentially becomes an enhancement factor in the flow law. So on the left here, we're showing a von Mises stress run with uncoupled damage and rheology. In the middle, we've coupled damage and rheology, and on the right are observations. And we see that we've greatly improved the fit on this area of the western ice tongue near the grounding line. But we're now overestimating velocities on the eastern ice shelf considerably. And this is likely because the optimization does not account for damage, and so our optimized temperatures are too high, and thus the ice is too soft. If we look at time series of mass loss from these different runs, we have uncoupled runs here in blue and orange, and the coupled run in green, and we see that all else being equal, applying this coupling leads to about a tripling of mass loss over this short time period. So while this shouldn't be taken as a projection because it's still untuned, this just illustrates how effective this coupling is. In summary, we find that the accumulation of significant damage across extensive parts of the ice shelf indicate that we really can't expect to model Thwaites Glacier accurately for more than a few decades unless we include damage in the calving law. We also find that calving criteria that account for both stress and damage match observations better than either do individually. And we find that coupling damage to ice rheology is necessary to reproduce the observed velocities near the western ice tongue grounding line, and future work will focus on including damage in our optimization. So I'd like to acknowledge funding from the Department of Energy and take any questions.
All right, next we have a talk by Ken Zhao on circulation melt interactions within glacial fjords.
All right, thank you so much. I'm really excited to be here. Fair disclosure, I'm a physical oceanographer, and I've already learned so much about ice from all of you. So don't hesitate to teach me some more. So this is work basically investigating ocean circulation near the margins of both Antarctica and Greenland. As you can see from a recent ice sheet mass loss in the last couple of decades, most of the ice sheet mass loss is around the perimeters of both the West Antarctic ice sheet as well as Greenland. There's definitely a lot of terms that go into this anomaly in the ice sheet mass loss around the perimeter, lots of ice sheet mass balance terms, but the leading contributor to the anomaly in some of these regions is the ocean forcing. So in places especially in Greenland, although the retreat, the ice sheet mass balance, the ocean term isn't a dominant term, the anomaly, if you just look at the anomaly, the ocean thermal forcing is potentially leading order. In Greenland, there's been more observations, so for the sake of this talk, I'm going to be focusing a lot on the fjords around Greenland. And of course, there are fjords in the Antarctic Peninsula as well. But hopefully I'll say enough general things that you can infer maybe some of the results to ice shelf cavities as well. So I'll try to define as much as possible as an oceanographer. I know some of these terms might not be within your expertise. So what is a glacial fjord? It's a narrow, deep, glacially carved valley connecting the open ocean to a glacier. And you could kind of similarly define ice shelf cavity, except the ice shelf cavity is also beneath some floating ice. And so just from a dynamical perspective, what drives circulation within a fjord? There's really two main drivers. There's a strong discharge plume, which in Greenland is a dominant effect in many places. The discharge rates can be, hundreds of meters, cubic meters per second, up to even thousands in some places. And basically, it's this discharge of fresh water at the base of a glacier near the grounding line, which is very buoyant and then rises up to the surface and entrains a lot of water in the process. So in doing so, it drives this strong overturning circulation, where this overturning circulation is the key to bring heat at depth towards the face of the glaciers and melt water away closer to the surface. You can imagine without this process, the glaciers would just be sitting in a pool of cold water, close to freezing point, and not be able to transfer all this heat towards the glacier. And so, the second thing I want to talk about too is the meltwater plumes. And this is kind of the focus of some of this work. But basically, although you have a strong discharge plume in certain seasons, near certain marine terminating glaciers, the meltwater plumes also do a lot. What that means is, you have warm water near an ice face, and that basically seeds a continuous source of plumes all distributed throughout the ice face. It's not as visibly observable as this central discharge plume, but it's all over the entire face, so its effect is also potentially important. And hopefully I'll show you that it's a leading order effect. So to investigate this question of how does ocean circulation influence glacial melt in fjords, I would say the preface to this is that kind of the conundrum here is that meltwater concentration observations, like the one that Andrew showed, seem to suggest that melt rates are about 10 times faster than our best models of this ocean-driven melt process. So there's an order of magnitude discrepancy that we're trying to better understand. So in order to do that, we set up the highest possible resolution model that we can afford. So this is within a fjord channel where the western boundary is the glacial face. So the horizontal resolution here is 15 meters, and the vertical resolution is 5 meters. And you can just get a sense of all the interesting dynamics that are at play here. There's boundary currents, there are eddies, there are lots of wave activity. And I would say like a dominant effect is this horizontal recirculation that you see. So, this is just a few samples at various depths, but definitely across most of it, you see this horizontal recirculation that definitely at the ice face, you can probably guess that like that horizontal velocity shear is going to contribute to some of the melt rate. Here's just giving you a better sense of what the hydrography looks like within an idealized fjord. So the temperature profile. Oops, I think I lost my cursor. Well, in the top left panel, you can see the potential temperature with, of course, the glacier is to your left. And so it's a lot cooler, a lot fresher at depth. And the overturning circulation basically shows that you're driving this inflow towards the glacier, and then this at depth, and then closer to the surface, you're driving this outflow. So that's kind of an important consideration. Again, that's how the heat is brought in. And coupled with this is a deep recirculation, which, in the previous slide, you kind of got a sense of that deep recirculation at, a whole range of depths. And so I'm going to focus on the overturning and recirculation and then hopefully tie that to the melt rates. So I'm going to highlight 3 cases. The first is the reference case, which has both a melt plume parameterization, parameterizing the process of a continuous source of meltwater at the glacial face, as well as the discharge plume. So you can see the discharge-only case has this shallower overturning circulation, where you're basically converting lighter classes of water into even lighter classes of water. And the melt-only case, it has this deeper overturning circulation. And then the recirculation, more or less, is this horizontal velocity that basically the highest, the high order interpretation is that as your overturning circulation strengthens, your deep recirculation also strengthens. And so, what does that do to the melt at the ice face? Well, you can see pretty interesting profiles of this, but again, where there's stronger recirculation is really where there's stronger ice melt. And just comparing like the reference, melt, and discharge only cases, you see that with just the discharge plume, there's a recirculation at shallower depths. And so melt is concentrated, higher up in the water column. And this, patches of blue that you see shaded there, it's just over a much smaller area than having the distributed melt source all along the face. So I guess directing your attention to just the overturning plot on the left, you can see basically if I decompose the whole overturning circulation into a case with just discharge and a case with melt only, that once I add both plumes, it more or less the overturning circulation is the sum of both of them, and that the melt only case, accounts for the majority of the deep circulation. So, I guess takeaways from this are that if you look at the deep ocean circulation, you care more about the melt plumes. Just to motivate this with some equations, I know no one can comprehend these equations in 10, 15 seconds, so I'm gonna simplify this a lot. And so, even this is kind of complicated, but just to give you some insight into this, the overturning circulation is primarily driven by a discharge plume and a melt plume. And you can imagine for, a lot of Antarctic cases, the first term is probably pretty small compared to the second term. That second term depends on horizontal velocity. And, this is hinting at the feedback. The recirculation, the second equation, depends on the overturning circulation. And this is based on a vorticity balance scaling, oceanography stuff. And then finally, the melt rate is a function of the recirculation and the overturning. And so, and that's based on traditional plume theory and thermodynamics. So you can get a sense by the color coding that there's definitely a feedback here. So basically, in summary, the dynamical process that I want to highlight here is that a melt plume can drive deep recirculation, which influences the horizontal velocity of the ocean right up near the glacial face. This drives melt, and further, this melt can lead to additional plume-driven overturning from the melt. And to give you a sense of how strong this feedback is, at our lowest resolution models of 200-meter horizontal resolution, compared to our highest resolution models, so going from about 200 meters to 15-meter horizontal resolution, this feedback accounts for doubling of the melt rates in our test runs. And the undercutting increase is even higher. So the rate of undercutting is like triple in some cases. All right, and so that's pretty much the end, but I just want to highlight some additional complicating factors. So once you take this and you put all these theories in real geometries, things do get a little bit complicated, but also kind of similar. So what happens is you see all these standing eddies emerge in fjords and ice shelf cavities. This is just highlighting some, so the red dots are kind of the focal point. So instead of recirculation, in this bathtub-like domain across the whole bathtub, you see it localized to certain locations. And so a 3D rendering is kind of shows you that, those vertical red blobs are where the eddies sit. And they sit there a lot, and there's some mergers. There's lots of interesting, ocean dynamics at play. And recently, the NASA Oceans Melting Greenland observed the first eddy just a few weeks ago, so that was super exciting. And so they do exist, and they might exist in other fjords and ice shelf cavities. And very finally, the ongoing process is to make these high-resolution models all around Greenland of these fjords, and hopefully in the near future, we will do some on the peninsula and other places as well. Thank you.
All right, next we have a talk by Dennis Wu on the development of a fixed-wing UAV for ice-penetrating radar data collection.
Hi, everyone. Thank you for coming. My name is Dennis. I'm working with PhD candidate Thomas Teisberg in Professor Dustin Schroeder's Radioglaciology lab. And I'm going to be talking today about my work this summer for Thomas on the development of a fixed-wing UAV for ice-penetrating radar data collection. Currently, ice-penetrating radar data is collected from large crewed airplanes. There's an example of what one looks like here from the University of Texas Institute of Geophysics. The flight time of one of these planes is around 6 hours, which is limited by the pilots and the crew. And downsides of this method of collection are a high fuel usage at around 1,000 pounds per hour and an overall high cost. One alternative that Thomas had worked on previously was using an unmanned aerial vehicle instead. on the scale of a 2-meter wingspan fixed-wing drone. Currently, we're flying smaller scale test aircraft, but we hope to build up to the drone on the right half of the screen, which is the Penguin B. And the benefit of the Penguin B is that it has a longer flight time at around 20 hours and a much lower fuel usage at around half a pound per hour. Overall, it is also much lower cost. So in other words, with this long flight time, a radar-equipped Penguin B could provide production-scale ice sheet surveys. So essentially, much of the same surveys that are provided now by crewed airplanes and at a lower cost. A significant challenge with this idea is that the UAV is much smaller than an airplane, which leads to the question, how do you downsize the systems? And it's possible to do this with a software-defined radio, or SDR, and a small computer. So part of what I worked on was making a functional radar system with a Raspberry Pi as a computer and an Edis B205 Mini as the SDR. And relatedly, we expect that a system like this might ultimately output around 100 watts of power, which is still relatively low. And so this leads to a second question: how do you achieve high signal-to-noise ratio, or SNR? We plan to address this with coherent summation and averaging, so summing phase line signals and dividing by the number of sums. Physically, this is possible by flying slower over the ice, which increases the time window over which we can coherently sum, and therefore increases the number of sums we can use. So the second part of this project was just verifying that the B205 was capable of coherent processing. So the first part of this project, miniaturizing a radar system, this was done in a field on Stanford's campus. Using the Raspberry Pi to control the B205, I sent out a chirp signal from 1 to 20 megahertz, mixed up to 325 megahertz, and bounced the chirp off the side of a building. This setup is shown in the picture on the right. The black heart holds the B205 and the Raspberry Pi, and then the B205 is connected via coaxial cable to the 2 white boxes, which hold copper bow tie antenna. The 3 colors in the image indicate the 3 most prominent paths of the chirp that show up in the received signal. So in green is the echo off the side of the building, in orange is the direct path between the 2 antennae, and in red is the internal path within the SDR itself. So here's what those signals look like at 30 meters away from the wall. At top left is the raw receive signal. Match filtering with the original chirp gives the output at top right. And in that graph, higher peaks indicate locations where the chirp was received. So I zoomed in to the part of the graph with the highest peaks, and that's what's at the bottom of the screen, and I identified them. So in red is the internal path, because no matter what distance this test was being run at, this peak always showed up at around the 160th sample. So essentially, this is the time of transmission. And then 4 samples away is the direct path. I'll get into the calculations in a second, but this indicates a total travel distance of around 20 meters in air, which is expected. And then the echo, which is what we really care about, is 14 samples away, which again is expected for this distance. For 40 meters, this is the data. It's the same graph setup. So you can see in the bottom that the direct path is 4 samples away, and the echo, what we care about, is 18 samples away. And then for 50 meters, finally, same graphs again. The direct path is 5 samples away, and the echo is 21 samples away. So the information on these tests is consolidated in this table on the left half of the screen. And at a glance, you can see that the measured sample offsets for both the direct path and the echo match up very nicely with what was estimated. The way I was getting these estimated values is essentially a unit conversion. So knowing the distance that the signal traveled and the signal speed, we can get the time of the signal, and then knowing the time of the signal and the sampling rate, we can get the number of sample offsets. So that's how everything was calculated. Finally, I converted the number of echo samples, so 14, 18, and 21, back into a distance estimation and plotted that estimation versus the actual distance I was away from the wall at the time of the test. You can see that graph on the right-hand side of the screen, and the trend line that fits these points is effectively a one-to-one line, which is great because it means that the radar system works, at least in a basic sense. So with this proof of concept of the radar system, the next piece of the puzzle was coherent summation to improve SNR. However, the big question was whether this was even feasible. The worry was that time delay errors in the B205 might offset the phase of the chirp such that received signals could not be coherently summed at all. An equivalent question to ask was, assuming for now that the received signals were phase aligned, would coherent summation with the B205 show a linear increase in SNR with the number of sums, as is theoretically expected? So to test this, I set up a loopback configuration on the B205, so only one copy of a chirp was received, and then I added enough noise that match filtering would not yield any meaningful result. Since radar systems are significantly affected by thermal noise, this was the type of noise used. And this is what the top row shows. So on the left is the individual signal with a lot of noise added, and on the right-hand side is the match filter output with no legible peak that you can see. And then I generated 99 more loopback tests, added noise to all of them, and summed and averaged them together one by one. So the end result of that, after 100 summations, is shown in the bottom row. You can see the benefit in the left, which shows the chirp coming through at around 5 to 10 milliseconds. That's where the signal is a little bit thicker. And a big benefit is shown in the match filter output, where you can see a very legible peak before 5 milliseconds. So for each number of sums, 1, 2, 3, all the way up to 100, I calculated the SNR by comparing the coherently processed signal with a quote-unquote ideal loopback test without any artificially added thermal noise. So that's on the left-hand side of the screen. And plotting the SNR versus the number of sums gives the graph on the right-hand side of the screen, which is a linearly increasing line, which is great because this is what we were hoping to see, and that indicates that coherent summation was successful with the B205 Mini. So in summary, this project was about making a functional radar system with a small SDR, the B205 Mini, and a small computer, the Raspberry Pi 4B, and verifying that coherent summation was possible with this setup. Things that are coming next in the project. The code needs to be modified to continuously transmit chirps and capture data. Antennae need to be placed into or on the wings of the aircraft, which will involve cutting them down to size and simulating the new shapes. And in addition, because the UAV is significantly exposed to sub-freezing temperatures, there needs to be a warming apparatus that can regulate the interior temperature of the aircraft within a range that all of the parts can function. And finally, one application of a radar-equipped UAV that Thomas and others in the lab are looking into is towards solar-powered gliders. So an example of what one looks like is in the picture, and this is the Aurora Odysseus model. The Aurora Odysseus is capable of half a year-long flights or more, even perpetual flight. And scaling a UAV up to a solar-powered glider is more conceptual right now, but we're keeping it in mind, and building a working radar-equipped Penguin B would certainly help with the scaling up process. So thank you very much for listening. I'd like to acknowledge my mentor, Thomas, advisor, Professor Schroeder, and also Anna and Nicole from the lab for their guidance on this project. And I will take any questions you have. Thank you very much.
Great. It's fun going after Dennis's talk because I really think that that development pathway from small fixed-wing UAVs to these longer duration UAVs is the way that will transform how we collect a lot of our ice-penetrating radar data going forward. So this talk, though, is about orbital sounding. My goal here is to equip all of you so that if you either have the thought or hear someone have the thought of why don't we do this from orbit instead, either in a CubeSat or like something we do at Mars, you'll know both what would make that hard, what would make that possible, and what are maybe interesting and appropriate questions for an orbital mission rather than one of these fixed-wing drones. So again, what we're talking about is ice-penetrating radar data. They make profiles like this. The plot in the middle top there are decades worth of individual flights by crewed aircraft, and they're gridded together into maps like that. This is how we collect this data. There's been a ton of progress recently in looking at all sorts of other things besides just ice thickness. We can look at ocean access, we can look at freeze and thaw on the bottom, we've detected groundwater, you can look at ice fabric, there's a lot you could do. And so this is good. This motivates why we'd want more ice-penetrating radar data and why maybe we'd want an orbital mission that could collect lots of it in a stable way. And these conversations tend to start with a thought like this. Okay, we've got decades of collecting data to grid together of crewed aircraft. And at Mars, you just have this, embarrassment of riches in terms of coverage and even repeat passes. Now the challenge is, so we're doing it at Mars, why can't we do it at Earth? It's a couple of things. One thing, there's no FCC at Mars regulating our frequencies we use. The Martian ionosphere is a little easier too, but there's also glaciological differences. So the simple mental model here is what determines how strong the reflections are from the bottom. This is how reflective is the bottom of the ice sheet. Is it water or not? Water's like 1,000 times more reflective than frozen bed. And how warm is the ice? So you can see in the plot on the top, when ice is very cold, like it is on Mars, you get like, a couple dB per kilometer losses. On the right side, you get like 50 dB per kilometer, 10 to the 5th per kilometer more losses. That's hard because it's warm here. Okay. But luckily, we do have a lot of data. So we're just trying to empirically answer how strong does your radar signal need to be? In other words, how strong does the reflection of the surface echo of the ice sheet need to be if you want to see the bottom? So we started with a bunch of Texas data, just subtracted the bottom from the surface. We threw all of this into a big tech triumphalist empiricism exercise of machine learning. We threw in initial data of thickness and velocity, geothermal flux on the bottom, modeled bed temperature, and then tried to predict how strong this difference would need to be. So you can look at the plot on the left and be like, all right, there's some areas sort of in the center where you need more power. You can have a nice cumulative distribution function on the right. And so you could imagine yourself saying, okay, if I want to see most of the ice sheet, I need a surface echo, I don't know, like 90 dB. This is a very strong echo. This is a ton of power. So you either need like a massively strong transmitter, like a giant antenna, or many elements in an array. So that's takeaway one. We need lots of power. Now, if we break it down by area, if you were imagining you might want to do a mission, you can imagine looking, okay, at the ice shelves, and you see the curve for the ice shelves in green up there. That's way lower. That's like 20 or 30 dB, right? So you can now say, okay, doing an ice shelf-centric mission would be easier than doing a grounded ice-centric mission. You can also see that the fast-flowing ice is a little easier, right? So you can see it's like, I don't know, 60 dB, 70 dB. So this is because the bottom is more reflective, because the bottom's thawed. That's great. And then, okay, you want to get in the middle, you want to get in cold regions. Now you're talking 90 dB again. Okay, fine. These are things we could imagine doing. And so the next thing you would find yourself asking is like, all right, if we need to get a more directive beam, maybe we want to go up in frequency, right? Even the antennas will be smaller. Now there's trades there. So the first thing, if we just look at areas where we have existing ice penetrating radar data collected at different frequencies, you can see that the required signal to noise ratio goes up. This is because losses are higher and it's rougher. This is just purely empirical. But this is sort of a light preference to go lower in frequency. Fine. Much more interesting, and this is, the provocative question to meditate on or talk about around a campfire tonight, is what is the geometric spreading loss of an echo from the bottom of the ice sheet? Maybe you were already talking about this last night. It's one of my favorite things to talk about. But the difference is if you have a radar signal and it comes out, it spreads out like a sphere, right? That goes like 1 over r squared. And if the reflection on the bottom is like a mirror, then it keeps going. That's 1 over r squared the whole way. If you go out and you get 1 over r squared coming down, and it's rough and it scatters, on the way back, it goes like 1 over r to the 4th, right? This is giant when you're talking about what is the difference between airplanes, which we fly, and orbit, whether your distance r goes like, losses go like r squared to r to the 4th, totally different scenario. The other thing this paper showed by MacKie is that if you have the bottom that's like a mirror, and you have those little yellow areas, if you imagine like taking a mirror and putting masking tape on it and then sandblasting it and taking the tape off, you only need like 5% of the mirror to be intact for it to still be mirror-like. So now the real question in frequency dependence is how does the change in your wavelength govern how much the bottom looks like a mirror? That's going to govern how things perform at orbit as a function of frequency. We don't understand this. This is very underappreciated. The other thing that can be a giant effect, given some of the other talks we've seen earlier, is if you have water inside the ice sheet, water in the fern, dolines, any amount of water, all of a sudden this frequency-dependent losses of the absorption and scattering become giant. So if you see down there at sort of L band, you can get like whatever, that's something stupid, like 600 dB or something. And then on the top, it's, fractions. So if you want to work in areas that are warm, the frequency dependence becomes giant. All right. So there's your frequency choices. So going down in frequency is good. It's mirror-like, good for losses, and much better if it's wet. Now, what do you want to actually look at? Well, one, you can flip that whole water thing on its head and say, okay, that like 50 or 60 dB of attenuation that was making it hard to see the bottom, that's a signal. So now you can imagine looking at seasonal changes of glacial water from an orbital system. And you could convince yourself that even these drones maybe can't get year-round observations, and you can see seasonal evolutions of glacial water. That's something you could do from orbit. Riley's poster highlights near-surface processes, and you can get these ice layers. So again, near-surface water refrozen in ice is probably below the resolution of what you're likely to get from your orbital radar, but we can do thin film models and know their effect, and you could probably see seasonal or interannual evolution of the near surface. That's something you could do from orbit. Again, on the theme of time series, Winnie Chu's paper showed that on the base of the ice sheet, the difference between winter and summer storage of water, again, expresses itself as a change in reflectivity. Again, you could do this with a drone if it went back, but again, an orbital mission can sort of coolly repeat itself. You might be attracted to look at glacial layers. Joe McGregor had this great compilation from Greenland where we looked at the large-scale structure, and anyone who's tried to correct for multiple seasons and multiple different radar systems know that it's a real pain. And maybe if we had an orbital system that was totally uniform, you could map it everywhere. Even more excitingly, we're working on approaches that use the glacial layers to do INSAR, but vertically. So as you get vertical distance changes, you can get the vertical component of velocity and add that to the horizontal component of velocity and get 3D ice flow. You can imagine doing this from orbit, but also the drones. It's tempting to talk about doing mapping. We mapped the surface of the Earth with the SRTM shuttle mission, so why don't we just throw it up there and map the bed again? Something you could do. It's challenging to see the bed everywhere. And the honest approach is that everything we use for the bed uses interpolation, including MacKie's geostatistical approaches. So whether an orbital geometry is really what you'd want to feed interpolation, or whether, if you go look at Thomas's poster, you'd rather survey for interpolation is an open question. If you're going to look at the bed, you might do stuff like MacKie's to try and characterize, bed lithology because it's a uniform data set. Maybe you'll do stuff like Eliza talked about earlier, try and look at reflectivity of frozen and thawed parts of the bed. But again, these are reflectivity signals, not geometry signals. Finally, we talked that ice shelves were easier targets from a reflectivity point of view, from seeing the bottom. Ola Kazandar had some work that showed that you could see from repeat flights of an ice shelf, you could see 500 meters of melt on the bottom of the ice shelf. So maybe that's a useful target if you are going to insist on doing this from orbit, is to look at differences of ice shelf thickness and finer scale stuff than you could see from altimetry and hydrostatic assumptions. Takeaway from all this, these are huge ranges. They're almost valueless. But if you look, the bottom row of ice shelves are easier, and the lower frequencies generally are higher SNRs, so that's a reason to not get overexcited about large arrays of high-frequency stuff. And none of this addresses clutter, which could be a real showstopper. And the clutter really drives you up in frequency, so you can have an array. But even the clutter itself may be near-surface quasi-specular stuff from the fern rather than traditional clutter. So this is omitted, but this is the other major concern. So anyway, with that in hand, hopefully you're ready to have spirited debates about orbital sounding tonight and every night.
Thank you, Dusty. Next, we have a talk by Datta on snowfall climatology in extremes over Antarctica, first results from a variable resolution CESM2.
Hello? Hello, WAIS. This is Datta, and I'm going to be presenting some first results from a variable resolution version of the CSM2 Earth Systems model over what I've been referring to as the ANSI grid. And this is work done in conjunction with Jan Leonards at CU Boulder, as well as Adam Harrington at NCAR. So firstly, to introduce the grid, this is a spectral element variable resolution version of CSM2. And CSM2, as contributed to CMIP6, was at a 0.9 by 1.2 degree resolution, whereas the ANSI grid is at a 1/4 degree resolution within the domain, and this is shown here on the right panel, and at a CMIP6 resolution outside of it. So this has also been rotated to provide coverage over maximum sea ice extent, which is shown here on the left. Now, if we would zone in on this very small part of East Antarctica, what I want to emphasize here is the way that enhanced resolution can capture more complex topography. The grid lines are the CMIP6 resolution, and the spectral element points for ANSI are shown here in red dots. So the current run that we have is from 1979 to 2014, and this is with observationally forced sea ice concentration and SST. And we're also producing 3-hourly outputs specifically to be able to implement AR detection algorithms. So for the purposes of this talk, I'm going to be mostly evaluating the outputs that we have, but also presenting some future experiments that we're going to be conducting over the remaining 2015 to 2020 period. So I'll be comparing with ERA 5 reanalysis, but then also using 2 versions of the coarser resolution CSM2 to tease out what is the effect of resolution alone versus what is the effect of resolution and forcing. And I'll be using the AMIP style model results, which have forced SST and sea ice concentration identical to what ANSI is using. And this is a 10-member ensemble. The other set of models I'll be using is the CSM2 lens, which is a large ensemble of 90 members, but this is where ocean and sea ice are allowed to evolve freely. So the first major difference is in surface mass balance. And I want to start off by emphasizing that although there are differences, the surface mass balance from ANSI is actually within 1 standard deviation of the ensemble mean for either AMIP or CSM2 lens. But we do see these pretty substantial spatial differences. And mostly in both cases where the grounded ice sheet shows higher SMB in ANSI, but shows much lower SMB over ice shelves and at lower elevations. The other thing that we can see here is that there's this really dramatic spatial difference here and here, which very likely has to do with the sea ice concentration and SST forcings that differ between the two. So here we're splitting things up in terms of snowfall on the left and surface melt on the right. And what I want to emphasize is the fact that snowfall here is much more variable along the ice sheet margins when doing an apples-to-apples comparison where only the resolution differs, whereas you see a great deal of difference when compared to CSM2 lens. Now with surface melt, what we're looking at here is total integrated surface melt in millimeters water equivalent from 1979 to 2014. Orange is showing AMIP, blue is showing CSM2 lens, and the black line is ANSI. And the shaded bars are 1 standard deviation of the ensemble mean. So the major takeaways here is that if we're looking at East Antarctica and the grounded ice sheet, we see a greater amount of surface melt, but it's within the boundaries. In ice shelves, it's substantially lower. In West Antarctica, it's higher, but again, in both the grounded ice sheet and ice shelves, but again, within 1 standard deviation of the ensemble mean for the similarly forced AMIP. But then in the Antarctic Peninsula, we see higher surface melt overall, both on the grounded ice sheet and ice shelves. And what we want to do is look a little bit further into the energy balance that produces these higher surface melt values. What I'm showing here is a comparison for both models and ERA 5 observations between 2-meter air temperatures, downward long-wave radiation and downward short-wave radiation. And one of the first things we can pick up here is that the warm bias, which was discussed the warm bias of CSM2, which is discussed at length at Donabasaglu et al. 2020, that remains in ANSI and is in fact enhanced. So here, when we're comparing with the AMIP model, the only thing that's changed here is the resolution, and in fact, ANSI is substantially warmer in summer. But if we look at the differences between in downwave long-wave radiation and downward short-wave radiation, we can see something else that's kind of interesting. Where we see enhanced downward long-wave radiation, you would expect to see a difference in total cloud cover, and which would also manifest itself as a compensatory increase in decrease in downward short-wave radiation over the same region. But that's not something we're seeing here. We're seeing enhanced downward long wave over East Antarctica at higher elevations, and we're seeing enhanced downward short wave radiation at the ice sheet margins. So we're going to have to tease apart what exactly is going on with clouds with a little bit more depth. And here we're not looking at overall clouds, we're looking at just low clouds. And what we can see here in the low cloud cover fraction from summer is that we have enhanced low cloud cover in both as compared to the AMIT model and the CSM2 lens model. So this is just an effect of resolution. Now if we look at the winter, however, we can see enhanced low cloud cover around the margins where you have enhanced topography in both models, but you can also see this enhanced low cloud cover around the ice sheet margins. This has been discussed in the AMIP simulations as well. But that can have a cumulative effect when you combine both a higher resolution and enhanced low cloud cover. So just to compare the sea ice itself, independently of the atmosphere, what I'm comparing here is what is forced on both AMIP and ANSI and what is modeled in CSM2 lens. And the major differences here that I want to point out is the higher sea ice cover that's present in ANSI right here in the Antarctic Peninsula and right around the ice sheet margin in West Antarctica, and also this really dramatic spatial pattern that happens in winter. So the major conclusion here so far is just that resolution matters, but so does forcing. And so for some future work that we're going to be doing for the 2015 to 2020 runs that remain is trying to set up a framework for sensitivity experiments where we can explore some of these connections between forcing and precipitation, and that includes both large-scale precipitation and extreme precipitation events. So one of the things that we're really interested in here is extreme events, and especially atmospheric rivers. And what I'm pointing out here is this is a figure from Gorodetskaya et al. 2014 that discusses a atmospheric river event that occurred on May 19, 2009. And I'm pointing out right here. That's where it landed, and this is from ANC outputs. And I want to point out the same point over here. And this is total cloud water vapor. And it's about to land right there. So mostly I'm just showing this to point out that the enhanced resolution has the potential to do a better job at capturing atmospheric rivers. And it's still going. Okay, well the other thing that's really interesting about this period is that there was from 2015 to 2020, is that there was a dramatic reduction in sea ice. And this is reported on by Parkinson et al. 2019. But the thing I wanted to point out particularly was that that she attributes the decline in sea ice to an interconnected global climate system. So as they tie the sea ice changes not to the circumstances in the vicinity of the sea ice, but also to events in the tropical and mid-latitude oceans. So fortunately, within the NERSS system model, we have a capability of sort of exploring some of these connections. And here what I'm showing is a moisture tag map that was first used in Wang et al. 2020 that we're going to be adopting and modifying. And what this is doing is choosing portions of maps, a portion of the globe, where we can connect a moisture source in the ocean to a precipitation event on the ice sheet. So this is something we're going to be implementing pretty soon, and looking forward to seeing what the results are. And I'll conclude here by just showing off a map of snow and melt over 2009 from ANSI, and I look forward to the discussion. Thank you.
Okay, and our final talk is going to be by Peter Washam on the evidence of recent ocean-driven grounding zone retreat at Cam Ice Stream Grounding Zone.
Hello again, my name is Peter Washam. I'm sure you're getting tired of hearing from me, but I've been tasked with giving 3 presentations, 2 of which are for group members or the PI of my group, Brittany Schmidt, who are either going to the field, Brittany, or are in a test to understand how isolation and effects like that impact astronauts. So the second person is Justin Lawrence, and I'm giving his talk today because he's in a NASA testing facility right now. So this presentation is an overview of the ice, ocean, and seafloor at the Cam Ice Stream grounding line or grounding zone. So yesterday I gave a talk on the crevasse circulation from CAM. So this is going to look at kind of like the overall site and what it looked like. And CAM ice stream is stagnant and has retreated since stagnation. So this is going to kind of look into the oceans or ocean ice and seafloor signatures of that. And here are just some wonderful faces of the Iceland team from 2019 and 2020. This is the full team in McMurdo Sound, and this is the group of us who went to CAM Ice Stream and worked with Antarctica, New Zealand. Here's a picture of ice fin beneath the sea ice in McMurdo Sound. And here's an overview figure of the ice, ocean, and seafloor at the site. So the site is this KISS 1 site up here. And you see it again is at the back of the Ross Ice Shelf. And shaded here is ice flow in meters per year. And you see CAM ice stream is stagnant, and then the part of it that's floating as part of the Ross Ice Shelf is slowly being pulled by the ice that's flowing around it. So at this site, we were about 3 to 4 kilometers from the grounding line point, as we can best tell. And you can see that the ice is shown in gray here, the ocean shaded as thermal forcing, or rather, as conservative temperature, with contours of thermal forcing is shown here, and then the seafloor in brown below. And what you see is the ice is generally flat. There's these interesting sort of concave formations and then these large crevasses. And yesterday I gave a talk that showed the current structure in this crevasse. So here it's shaded as conservative temperature. But what you see is you have a 2-layer water column here, which is really interesting. The top is very close to the freezing point, and the bottom or the lower layer is still quite cold. It's only up to about 0.25 degrees above freezing, and then there's this really nice thermocline separating the two. And shown here are some really cool images or sonar, visual or sonar images of what the ice looked like. So it ranged from sort of these ripple formations here to sort of more golf ball like scallops, and then here's some marine ice formation going on. And then the seafloor, there were these really nice imprints left from the crevasses, and the crevasses are all moving sort of to the right. So these imprints align with these crevasses labeled here. And here are some images of what the seafloor looked like. So here's a compass plot on the left showing the ocean currents in centimeters per second. And this is a tidally driven environment. So with the sort of the currents being sort of east, northeast to west, southwest. And they're moving at speeds up to about 15 centimeters a second, and all of that is shaded by the depth here. You can see, and then that crevasse that I showed data from yesterday, you have a mainly southward flow. But interestingly enough, there was an ocean mooring that was deployed, and sort of a mean current was taken out of that, and these ripples in the ice are orthogonal to that mean current. And then I'm a physical oceanographer. I'm going to focus mainly on what the ice and ocean are doing. I apologize. I'm not going to give a ton of insight into what the seabed is doing. So here are some sonar images of those ripples in the ice base from melting, which are really cool. And then some images of what the seafloor looks like. So here are profiles, vertical profiles of the hydrography from each dive. So it's sort of this lower water column below the ice base, the ambient ice base, And then this blue data is from the crevasse, so it's on a different scale you see there. And here is showing thermal forcing, salinity, dissolved oxygen, turbidity, and then current speed, just the magnitude of that. And there's this beautiful two-layer system at the site with this upper water column and then this lower water column, the upper being colder and fresher, the lower being warmer and saltier, and then this picnic line separating the two. So salinity is mirroring the temperature, and then the dissolved oxygen is inverse of that, and we understand that to be due to meltwater input raising the oxygen in that upper layer, and also raising the turbidity. So as the ice melts, it rains out sediment, and that's sort of being suspended in that upper water column. And so this structure varied in strength due to the tide. So when you had stronger tides, basically you mixed the two layers up more, and they were less stably stratified. And then during weaker current speeds, the opposite was true. And this here on the right is a TS diagram of the data. You see that the lower layer temperature and salinity is pretty close to the high salinity shelf water end member, so that's water formed out in the Ross Sea polynyas that then circulates beneath the Ross ice shelf, and you see it's pretty much reaching the grounding line or close to it in an almost undiluted form, which is following results that Begman et al. Found near the Willans grounding zone. And if you follow this Gata line down, or melt line, you can see that all the data fits it very nicely, and that shows us that we have two water masses mixing, that being high salinity shelf water and then glacial meltwater. And you can partition the data to see what percentage of glacial meltwater is in there. So the lower layer is somewhere around 1 milliliter per liter of meltwater, and then this upper layer is around 4 milliliters per liter. And finally, here is the data from the crevasse, shaded as thermal driving. You see that, and then there's all these really cool images of what the ice texture looked like. So moving up, you move from these sort of scallop formations to this point, which is labeled C here, where you begin to see this fuzzy marine ice. However, this marine ice is below the supercooling horizon, which means, or which shows us that either that horizon's moving up and down with the tide, or the whole system is moving upwards as the ambient ice base melts upwards. Above that, you see more fuzzy ice in the supercooled layer that is indeed actively freezing. You have these weird stalagmite sort of kind of formations up here. And then on the other side, you have at G and H sort of more vertical runnel-like features. And then below, you get back down to those scallop formations. So I thank you for your time. All this work could not be done without all of the individuals listed here and many more. But our group at Georgia Tech and who are transitioning to Cornell couldn't be more happy with working with the ANZ program and the collaborators in New Zealand, of which we have more work planned this coming year back at KM Ice Stream. Thank you for your time.
All right, thank you to all of our speakers. Could we get our in-person speakers up front for the discussion? Well, to start us off, I have a question for Ken. How do you think that your models would translate to Thwaites Glacier, and do you think that differences in ocean circulation could be responsible for the discrepancies in calving modeling that Trevor found.
Thank you. A super interesting question. As a caveat, I have not done very realistic simulations of Antarctic ice shelf cavities. I do have some very idealized work of Pine Island from 2019, with similar ocean stratification because they're adjacent. Definitely the wider ice shelf cavities compared to the fjords, there's more open ocean connectivity. So the relevant length scale is the deformation radius in the ocean, which is about 5 kilometers in this area, which means that the open ocean currents are allowed to come in much more readily because the ice shelf cavities are much wider than that 5 kilometer scale. So things like tides matter a lot more, which I haven't considered. I would say generally speaking though, the underlying phenomenon, the dynamics of overturning recirculation and the recirculation deriving this feedback between melt and horizontal velocities is going to be relevant there as much as it is in Greenland. Yeah, I'm really excited to maybe do more realistic simulations of ice shelf cavities in the near future.
Can I quickly add to that? If you can hear me. So one of the things that's really missing in our current formulation is that the ocean thermal forcing in the ISMIP-6 data sets only goes to 0. So there can be no marine ice secretion. And so more sophisticated modeling and observations like Peter's would be really great to see if there's any of these rifts that are actually freezing shut. And on the flip side of that, if there's enhanced melting within rifts is really important. So.
Hello, yes. I have a question for Tree. Thank you for the very cool talk, and I was very interested in your work you wanted to do with the atmospheric rivers. And I was wondering, have you looked into to see what the specific humidity behavior is with your ANSI product? And also the second question I have is, how does the ANSI compare with like other regional climate simulations, like from RACMO or MAR, in regard to like surface mass balance processes?
Well, so for the first question, I didn't include this just because of space, but latent heat flux is slightly higher in ANSI, and it's not compensated for by sensible heat flux. So this is just an analysis that's been kind of started recently, so there's still a long way to go. But in terms of comparisons with regional climate models, so some great work done by Devin Dunmeyer in the same lab that I'm in. She has been looking at CSM2 itself compared to RACMO. And in fact, it's higher. So, ANSI is even higher than that. So SMB values are generally going to be higher. But the spatial differences are something we're going to be exploring further. Kind of additionally, I was going to point out, but regardless, it's within the 1 standard deviation of the CMIP6 catalog. So it's acceptable, but a little high.
Thank you.
I had a question for Ken. I was wondering if you had, or if Ekman was a consideration for you at all, or if the circulation was too constrained by fjord geometry, or what you were analyzing was at too small of a scale, and if you see it possibly playing a role in future analyses.
Sorry, could you just clarify the constraints by?
Either just the scale at which you're analyzing, was it just too small for Ekman to play a role, or was it otherwise constrained by the geometry of the fjord?
I guess, sorry, there's a little bit of feedback here, but I think maybe we can talk more offline, but the geometry of the fjord, which is what I got, is definitely a first order player. I think for getting accurate bathymetry near fjords and ice shelf cavities, that is probably very few things are more important than that. And I think among other things, we discovered that eddies are basically the complication to the ocean circulation within these areas is definitely very much flows along bathymetry and kind of hugs and forms these standing eddies where it's the deepest part of the fjords. And definitely the kind of eddy focused recirculation is a topic we're exploring now, which is especially if the eddy is in this bowl really close to the glacier, most of the horizontal velocities are eddy-induced. And so bathymetry influence circulation is definitely, there's nothing more important than that. Thanks.
Hi, I have a question for Tree as well. So Tree, my question for you is, you mentioned that you're interested in using your new ANSI model to look at extreme events, including atmospheric rivers. And one thing I was wondering about is that it looks like the source region of atmospheric rivers is outside the high resolution region of the grid that you're using. And so I was wondering if you expect that to have any impact on the way atmospheric rivers are then represented when they make landfall over the Antarctic ice sheet, and whether that might differ from other extreme events that have a source region closer to Antarctica.
That's a really interesting question. It's kind of impossible to do a 1/4 degree resolution over the entire Earth, and if I could do that, I would absolutely do that. But if I think that the resolution is what the resolution is going to do, and surrounding the ice sheet itself it's able to capture some of the interaction with sea ice. But I mean, yeah, it remains a problem. The fact that there's going to be more interactions over sea ice, like we could see the differences. Even between AMIP and ANSI. And a lot of that is that even though the same sea ice is forced, you have a lot of moisture processes that are going on over the ice sheet, which are captured at high resolution. So yeah, there are going to be differences.
Peter, do you want to go ahead and ask your question?
Yeah, sure. Hey, Ken, good to see you. It was a great talk. So I was just curious because I didn't see any values for the current speeds. Do you expect that these eddies are going to be rotating faster than the sort of estuarine buoyancy-driven flow that would normally be driving these fjord circulations?
Yeah, great question, Peter. There is basically relative to the mean current speeds of kind of the bathtub case, which you can see, velocities of up to 15 to 20 centimeters per second in the horizontal. And, you can work out the heat, the thermal transfer associated with that velocity is already much higher than the low resolution cases. And with eddies, you can, see something like double that. So up to 30 centimeters per second, pretty close to the glacial face. Definitely depends on whether an eddy is expected close to the glacial face. So, I'll cite like one case, Jakobshavn seems to have this very strong persistent eddy really close to the glacial face. And the one that NASA observed a couple of weeks ago was in Torseskadak Fjord, which is in central West Greenland. Also very high velocities. So hope that answered your question.
Great talks, everybody. Thank you for your talks. I had another question for Ken, so I didn't want to inundate just you with the questions. But along the lines of the questions that everyone else has asked, like, you mentioned not incorporating tides, and winds can drive circulation and other things outside of the fjords. And it looked like you'd tested this at multiple places around Greenland already. So I was wondering how well your results match some of the observations, or like, are there places where they match really well and places where they don't match really well of what we've observed or what you would expect from those fjords? And if that like tells you a little bit about how important the glacier melting and these eddies might be in comparison to some of these other factors in those fjords in comparison to other fjords.
Yeah, absolutely. That's a great question, and I think the modeling is great, but in a vacuum, not considering observations is definitely a mistake. And thankfully, due to the NASA Oceans Melting Greenland mission, which has been dropping 300 plus probes every year for the last 6 years, we do have a wealth of data to compare to. And so the main source of data that we're comparing to is stratification, which is temperature and salinity outside of the fjords, as well as inside the fjords. And so the stratification inside and outside vary by a lot. And so they match observations relatively well. I think the major discrepancy is that internal to the fjord, and this is kind of maybe motivated by some of the results I showed, there's a lot of variability. There's way more variability than we might have initially appreciated. So you can imagine if 2 or 3 probes were dropped in a single fjord, well, the fjord state changes depending on where what time you sampled, whether subglacial discharge was strong or not at that point in time. Various other factors that can, on just like a point sample vertical profile, you can get a multitude of different signals. And in fact, for the discovery of the standing eddy, you see the variation across the fjord over a few kilometers distance was pretty significant, enough to tell that an eddy existed there. I think it's within the error bars, but it's also, much more of a robust conclusion if we went and measured, did more ship transects within fjords, which is pretty difficult. So, I hope that answers your question.
Are there any locations where it matches better than others that you can think off the top of your head?
I guess so far I'll answer the flip side, which is the places I think that match the least are where there are strong outbursts of subglacial discharge. So, subglacial discharge is very intermittent. It ramps up very quickly in the summer months. Goes from nearly 0 to, in some places, peaks up to thousands of cubic meters per second over a span of, weeks to months, and then drops back down and then goes back up again. And so you can imagine the ocean feels that. And so really to capture that variability, you'd either need to do a lot more sampling in observational space or, have better models as well.
It looks like we have a question from Andy.
Yeah, hi. Hopefully you can hear me, Peter. That was a really nice data set that you showed. I was really interested that you could see the tidal fluctuations, and you mentioned that you could actually see a change in the stratification across that tidal cycle. And as you mentioned, we usually think of the overturning circulation as being buoyancy driven, but I was curious as to whether you could get at whether mixing due to waves or other processes could also be a way to modify waters from the denser classes to the lighter classes.
Thanks for the question, Andy. So let's see. Yeah, the picnic line in the ADCP data was super noisy, which suggests that there's mixing. There was a turbulence resolving thermistor deployed that showed mixing occurring across the picnic line. If you look at the Richardson number, it's really stable at times and it's not so much at other times. But what's interesting is, and I'm taking your question a little further than where it was intended, but the buoyancy driven flow there is north-south. So like along the coast, and then the tides are east-west. So you have like two different systems kind of going along, but certainly tidal mixing is happening between the two layers. And we were hoping that we would be a little closer to the grounding line, so the water column would squeeze and we might find a tidally mixed zone, like a fully mixed zone. But, well, you get what you get, you know?
That's great. Thanks very much.
So this is for Dusty and the two modelers. I mean, you kind of, Dusty, you brushed over clutter at the very end, and you were like, well, this could ruin everything. And then the two modelers were explicitly modeling something that gives you a whole lot of clutter. Is there any way to actually potentially leverage the clutter signal, either, I guess, in drones, going back to Dennis's talk, or in orbital platforms to map damage directly or something like that? You know, leveraging the noise as some part of the signal.
Yeah, I mean, I think you can definitely characterize near surface roughness, crevassing damage, all from, you know, to your point that what is clutter can be one person's clutter is another person's data. I think, you know, in this particular case, the way you would deal with clutter in an orbital platform gets sort of deeper into these implementation choices. Like, you can very quickly get into arguments about how many spacecraft you need in an array to get good side lobe patterns. You can get into synchronization problems. You can get into problems of should your array evolve over time. There's a great deal of variety and creativity that can be brought to bear on the clutter problem. But if you don't see the echoes from the bottom, no creativity will save you. And so I think, you know, that was the reason it was de-emphasized there. But I do think, and if, for those of you who look at sort of Croesus data or standard data products that have been focused, the focusing takes away the clutter signal. And so if you are a person who's interested in near surface effects or crevassing effects, your signal's already gone. And so you should get into more raw data products where you can actually see those effects. So I think that is an excellent point of another under-tapped resource.
Well, I have a question for Dusty and Dennis. What do you think would be the most optimistic timelines for potentially having sounding from orbit or with the UAV? I don't know if Dennis is here. And do you think that manned aircraft will eventually be phased out, or do you think that it will still play an important role in ice sheet observation?
Yeah, I can talk about the UAV. So I guess as for a specific timeline, we're not exactly sure, but right now we are working on kind of like a stepping stone to the final UAV that we hope to use. So we're going to be conducting field tests fairly soon, hopefully by the end of this year. And then for the second part of your question about manned aircraft, I would guess that with the UAV, there's still certain parts of, say, like Antarctica that are hard to get to. And so in that sense, manned aircraft might be really useful. Yeah, and then Dusty can go.
Yeah, I mean, I agree. I think we'll get, assuming COVID relents ever, we'll get some field testing initially done, I think, in this academic year. And I think in 1 or 2 iterations from that, we'll have like a functional drone that can do sort of a baseline level of sounding. Orbital's harder. You've got the cycle of NASA proposals. And so, I mean, as a person, like a radar sounder nerd, it would break my heart if we don't ever toss one up there. But I think, you know, the time scale is much longer, and the pacing is less regular. But I do think we'll totally obsolete people on planes before too long.
Yeah, I guess I kind of wanted to follow up because the question is an excellent one, and I think myself and working with KU, the Croesus folks, were actually flying the snow radar, a miniaturized snow radar on board of a medium altitude, long endurance drone. And so I think that it's really interesting that now we're kind of getting to this point where we're trying to move away from crewed aircraft and trying to do more unique surveys, think outside the box a little bit. So I think it's super great to see what Dennis is working on and I would love to have a chat with you at some point. I'm curious at this, where you are now, what sort of expected size of your payload is, and the weight and things like that, and with your flight speed, what is your target for sort of acquisition of, say, a single flight? How far do you think you can kind of survey on a single flight? I realize that you might be a little bit in the infancy or in this process, but I would love to hear it.
Yeah, I mean, as you say, we are a little bit in the infancy of the process. We haven't actually run a flight yet, but as I said, I think the flight time of the UAV is like approximately 20 hours, and so the hope is to like almost or completely match what's completed by an aircraft right now. And then as for the payload, I'm not quite sure as to like the exact specifications of what it would be. I believe that the maximum payload is on the order of around like 10 kilograms or something like that. But that's something to be optimized because like the heavier the payload, then we can't go as far with a heavy payload, essentially. But yeah, I'd love to talk more offline about this with you.
Yeah.
It'd be awesome.
Thank you. Thank you.
And I'll add to that that this is, you know, like Dennis presented, who's a very impressive undergrad, we should point out, that it's a development pipeline and that we're partnering with these folks who do these long duration stratospheric aircraft. So once you solve the problem of integrating antennas into the wings, moving towards these sort of near continuous observations, I think is the eventual arc.
And just a follow-up, so what is your kind of target altitude? Is it low altitude or is it pretty high?
So for these platforms that Thomas is addressing in his poster and Dennis presented, I think these would be much lower altitudes than you would imagine a person going to the field capable of doing. I think what you might imagine a season-long snowmobile-based survey or a smaller sort of Twin Otter scale survey. Once you move into these stratospheric aircraft that can stay aloft for months, then you're in the stratosphere, but that gets you more or less what a satellite would get you without launching a satellite, and you're below the ionosphere, which is super important. But I think they're two different use cases.
Yeah, I agree with all of that, and I think there's the potential right now is we gotta strike while the iron's hot and kind of get in at the ground level and look at all the different ones. So thank you both.
Yeah, thank you.
I don't have a question, but I just more wanted to make an announcement. The NSF Polar Programs postdoc awards were just announced, so I wanted to make sure while Ken's up here that we congratulate him on winning one. So if you'd give a round of applause.
Well, congrats, Ken. We have a question for Trevor. Can we ground truth any of your historical damage estimates with repeat airborne cluster? Is there hope to take the damage concept back to a direct observable?
Yeah, absolutely. So in this formulation, damage is just the ratio of the crevasse height to the total ice thickness surrounding the crevasse. So you could absolutely do this with observations. Whether or not that conceptual model is really great is, I guess, an open question. And I think Sam Kachuk's poster talks about that. Another thing that would be really helpful would be to know the initial spacing and depth of crevasses as the ice passes the grounding line. Currently, we just use the Nye zero stress condition to initialize crevasses, and then damage evolves based on stress and strain and melting. But I think there's got to be a better formulation for crevasse initialization that we could use, and observations would really help with that.
Well, thank you. Are there any final questions? I think we're almost at time. Great. Well, another round of applause for our speakers. Thank you.